So thank you all for coming, and thank you also to the physics demo lab staff who work several hours getting this all set, and it's actually a process that goes through the week leading up to this. So I'm going to tell you about accretion, which is actually a process that pervades many things in astrophysics, and it's actually a concept that's also important in meteorology. If you want to induce a cloud to rain, you can seed it with microparticles onto which little tiny droplets will start accreting, and then they'll accrete more droplets, and eventually they become heavy enough to fall. So it's sort of the process of gathering material, and it acts on many scales and in many settings. I'm going to mostly tell you about how it works with regard to black holes today, because that's where most of my work is done, but I also think it's among the most interesting cases. So this is just an artist's conception of gas swirling into a black hole. It's not a bad guess for how these things likely work, though, so it's a good thing to sort of keep in mind as we go forward. Now, this is a movie made over about 16 years. This is not an artist's conception. This is an actual movie made of optical observations of the center of our galaxy. These are stars, so things that are glowing at several thousand degrees. And you can see that they're orbiting something that you can't see. So what are they doing? They're orbiting the black hole at the center of the Milky Way. And watching these orbits is partly how we know that there's a black hole there in the first place. This is done using a very cool technique. If you have noise-canceling headphones, you know that the way those work is they sample the noise in the room, and they add the noise that's required to just cancel that out. This technique takes a big sheet of glass and a huge telescope and deforms the mirror in just the way required to edit out the atmosphere. So you get this wonderful unblurred image that allows you to see into those special scales close to the black hole. Now, as nice as that is, those stars are only coming tens of thousands of short-shield radii from the black hole, which isn't that close. If you want to get closer, you need to look in X-rays. Before gas falls into a black hole, it gets up to millions or tens of millions of degrees. And then it glows not in optical light, but in X-ray light. And so if you want to do this, you have to use orbiting observatories because X-rays don't penetrate our atmosphere. And one of the nice ones, because it's very flexible, is called SWIFT. And this is a NASA mission that was built in part with help from Penn State. And the University of Michigan actually became a partner in this mission last year. So we have some priority access to this. So if you come to Michigan and major in astronomy, you have the opportunity to point a NASA orbiting observatory, which is pretty good, I think. So my group uses this a lot. This is work that's led by a recent postdoc. Her name is Natalie Degenaar. And this is a composite image of the center of the galaxy again. The material in blue is the most energetic. The material shown in red is the least energetic. X-rays don't have color, but we can borrow the same sense of energy that we have in optical light and assign X-rays colors that way. So that's what we've done. And so there's a lot happening at the center of the galaxy in X-rays, but here is the central supermassive black hole, about 4 million solar masses. And so what Natalie does is she takes an image of this region every single day with SWIFT. Isn't that great? You get to look at it every day and see what's happening. And so we've been doing this for several years. So here's time on the x-axis from 2006 to 2012 shown on this graph. And then on this axis is the intensity of the light from our central black hole. And what we were looking for were occasional flares. These are accretion events where a little extra material accretes onto the black hole and heats up in X-rays just before it does. And we think this is pretty exciting, and it's telling us about the regime close to our own black hole, which is very nice. But our own black hole doesn't accrete a lot of gas. It sort of barely snacks on crackers. The ones that are really interesting are at the buffet and totally gorging themselves. And those are the ones we want to talk about, of course. So this is very interesting, but I'm going to talk about something different. To appreciate the scale on which accretion can act, I think we have to look at some of the largest things that we possibly can. So this is an optical image of a cluster of galaxies. It's the Perseus cluster. Every point of light that you see here is a galaxy, not a star. Okay? A rich cluster of galaxies like this can comprise hundreds or thousands of galaxies, and they're all going to fall toward the center, which happens to be here. Now, the funny thing about galaxy clusters is that although you can see an awful lot of mass sitting here because there's an awful lot of galaxies, right? It's not most of the mass. Most of the normal matter is actually in very hot 10 million degrees or higher gas. And then that's even dwarfed by matter that we don't know very much about, dark matter. So the light that you can see is actually only a small fraction of what's in that cluster. If we zoom in to this cluster galaxy at the center, Perseus A it's called, here's what that looks like. This probably looks a lot different than the mental image of a galaxy that you probably carry with you. That kind of galaxy might look like this. This is our nearest, nicest neighbor. This is M31. It has this spiral structure that we all like when we think about galaxies. It has an interior bulge. There's some dust lanes. It's a beautiful galaxy, and this is sort of what we think of when we picture a galaxy. But this is the one that's sitting at the center of the Perseus cluster, and it looks this way because galaxies are falling in and affecting it, but it also looks this way because of what the black hole at the center of this galaxy is doing. So this is the optical image of Perseus. This is the X-ray image of Perseus. All the galaxies go away because they don't glow very brightly in the 10 million degree gas that the X-ray image samples. But you can see that there's this soup of hot gas pervading this region, and if you look closely, you see there are these arcs that look like they're sort of bubbles emanating out, almost like a lava lamp, right? The black hole at the center of this galaxy is blowing these bubbles. In different episodes, it's ingesting a lot of material and then throwing out radiation and jets of matter and pushing around the bulk of the normal matter in this huge cluster of galaxies. So one tiny black hole at the center is affecting this cluster, and clusters the largest gravitationally bound objects in the universe. So that's kind of amazing. That's the power of accretion. To put this in a little bit of perspective for you, if we were to scale this sort of phenomenon to the Milky Way, well, our Milky Way has 1.5 times 10 to the 12 or so solar masses worth of material. That's 1 trillion solar masses of material. But our black hole has a mass of only 4 million solar masses. There's an enormous contrast, right? Our black hole is roughly 1/millionth of the mass in our galaxy. So very odd that it should have this huge effect. If you want to think about this on a local scale, if we say Ann Arbor has a radius of about 10 kilometers, which I think is actually a little bit large for the truth, 1/millionth of that is a centimeter, which is like a marble. So imagine a marble having the ability to affect the weather in Ann Arbor. And that's the power of accretion. If that marble were a black hole and we're eating a lot of gas, that would be the case. So really, when we think about accretion, part of what we're trying to understand is how does something so small affect things that are so large and in profound ways? To understand the impact that accretion has, we have to backtrack for a moment and think about energy and mass in a different way. And of course, Einstein was the one that helped us to do that. His famous equation, E equals mc squared, tells you that you can convert energy into mass and mass into energy. And as odd as that sounds, we know that it happens all of the time in nuclear reactors and in particle physics experiments. We see it happen. It's absolutely true. Quantum mechanics is the best tested theory that we've got. So even though this is strange, it's undoubtedly true. And the best possible use of E equals mc squared is, of course, starships. And I'm sure that many of you know that the Enterprise is powered by taking matter and antimatter and annihilating it together and getting energy out in a reaction that's 100% efficient. If you take an electron and its antiparticle, and we can make those in particle physics experiments. There aren't many in the present day universe because when they interact, they disappear, but you can make these. And if you take an electron and a positron and put them together, they completely annihilate and you get two very energetic photons out, closer to what we think of as pure energy. So that's a 100% efficient process. So if we think about different processes that are important in the universe or on Earth, annihilation uses 100% of mc squared. Accretion is the next best thing, and that's how you get something very small to affect something enormous, because you can harvest tremendous amounts of energy when you accrete things onto a black hole. 10 to 30% of the energy locked up in the mass can be liberated through the process of accretion. That's far better than fusion, which I'll remind you we can't do in a stable way yet, although maybe you saw that Lockheed thinks their skunk works will have fusion reactors on the back of semi-trucks within 10 years. Sounds good. Fission is what we do in a stable way, but this efficiency isn't realized because you're taking the heat energy and transferring it to water, creating steam, so the efficiency is actually lower than this. This is the efficiency in the nuclear reaction. And of course, fossil fuels are millions of times less efficient than that. So you can appreciate this is pretty special. It's the next best thing to what you have on the Enterprise. My Enterprise, anyway. To help you understand a little bit more how dramatic that impact is, let's think about something that's a little bit less extreme than a black hole to start with. Let's think about a neutron star. It's the ember of a very massive star that exploded. This is an X-ray image made by the Chandra X-ray Observatory, kind of a sister mission to the Hubble Space Telescope. And here, blue light is encoding iron, red light is encoding oxygen, and the green light is encoding silicon. We could have done that in a different way. That's just the scheme chosen for this. Now, you've heard Carl Sagan say that you're stardust, and you might know that by mass you're about 70% water, which means that you're a lot oxygen, right? Oxygen was not made in the Big Bang, only hydrogen and helium were. The elements that you're made of were made in stars, and should you ever doubt it, look here. You can see this is how it happens. It's made in very massive stars that explode. That material is spread through galaxies, and in different settings it can condense into planets that might eventually give rise to things like us. So this is really where you get it. Now, if we watch this explosion for 10 years, we would actually see it expand ever so slightly. That's been done. This thing here in the center is the interesting bit, though. That's the neutron star. To appreciate what we're talking about, we're taking something that's as massive as our sun, or maybe twice as massive as our sun, and shrinking it down to this size. It's incredibly dense. A state of matter likely exists in the center of neutron stars that we don't fully understand yet, though we're trying very hard to characterize it. And it's something that you can't get your hands on via any earthbound laboratory. So these are not black holes, but they're the next best thing. They're extreme objects where gravity starts to deviate from what Newton said. Now, if we actually put a neutron star on top of Ann Arbor, it would quickly suck the rest of the Earth around it, and it would be all over. The neutron star would continue on happily because that's kind of just a snack for a neutron star. Not a big deal. So the nice thing is, they're very compact. They're about 6 Schwarzschild radii. Remember, the event horizon of a black hole is 2 Schwarzschild radii. So these are things that are just a little bit bigger. So they help us to do some experiments with accretion, but not have to deal with the black hole yet. Now these objects were discovered in 1967 by a graduate student, Jocelyn Bell Burnell. So these were discovered by a leading woman scientist. Unfortunately, you may know that her advisor and his friend took credit for the discovery and got their Nobel Prize without her. But this was discovered by a woman, the existence of these things. Now, apart from accretion, these illustrate something rather interesting. And it's conservation of angular momentum, which is very important for many things in astronomy. The orbit of the Earth around the sun, important for accretion as well. And so, if you imagine a star during its sort of normal, healthy lifetime, and we're going to let it shrink down and become a neutron star, we can start with something like this. And as that shrinks, it starts to spin a little faster. And then as it shrinks more, it spins very quickly. This is just angular momentum conservation. It's the same thing that you see when a figure skater is twirling with her arms out and then brings them in and spins faster. Now, I could have done a demonstration with that, but I hate spinning, and so we're using this cool sphere instead. But the point is that angular momentum is conserved, so neutron stars spin very quickly, and they're some of the most stable clocks in the universe as a result. So let's imagine we have a neutron star. We won't put it too close to Ann Arbor. And let's say this little piece of chalk is actually a marshmallow. The mass of the marshmallow might be 10 grams or 0.01 kilograms. Let's say we've got a nice, healthy neutron star that's about twice the mass of our sun. This is the equation here, gmm over r. G is Newton's gravitational constant. Big M is the mass of the neutron star. Little m is the mass of the thing you're going to accrete. R is the radius or distance of interest. At infinity, this has got a gravitational potential of 0, depending on how you set your 0 point. By the time I bring it to the surface of our star, it's going to have a negative potential energy, which means that it's incredibly bound. But energy is relative, so I can swap pluses and minuses. What I want you to appreciate is that by the time it gets to the surface, it's going to have changed its potential energy into kinetic energy. You're going to have something moving incredibly fast, hitting the surface of this compact object, and you probably don't have too much trouble believing that you're going to get a lot of energy out of that interaction, right? That's the total energy available. Accretion liberates 10% by changing a little bit of this kinetic energy that's transferred out of potential energy and making that into radiation. This amount of radiation that would come out if we were accreting a marshmallow onto a neutron star, this is about equivalent to a Hiroshima bomb. So accretion turns marshmallows into very dangerous things. You probably didn't realize what you were holding on to before, right? But that's what accretion does. And when we think about its impact, we don't think about energy. Really, we think about how much light's coming out. So if we start with E equals mc squared, the amount of energy that comes out per unit time is what we call power. That's energy per time. And that's going to be related to mc squared by just considering how much mass I'm supplying per unit time. How many marshmallows do I throw onto the neutron star or onto the black hole? And when we think about the power that comes out in terms of radiation, we then call that luminosity. So the luminosity that we get is going to be 10% m dot c squared when we're accreting matter onto a black hole. So, I gave you this example of a marshmallow that gives you a Hiroshima bomb worth of energy. We're going to be, if we have a supermassive black hole, we're not going to be dumping a marshmallow on inadvertently and fairly randomly and not very often, we're going to be dumping on an entire star every year. And when you do that, you get out tremendous amounts of power, and all that radiation is going to shape its environment, including the cluster gas, the very largest scales, because radiation can push on gas and dust. And if that seems weird, I assure you it works. This is an artist's conception of the Japanese Space Agency's Icaros mission, which had a host of different experiments on it, but it found its way out into the outer parts of the solar system by deploying this huge solar sail and letting radiation from the sun push on that sail. Now, if you remember the terrible Star Wars prequels and Obi-Wan's offensively bad ship, it had a similar sort of solar sail on it that he deployed. If you don't remember this, I'm actually glad. That means maybe you didn't watch the movies. But this even found its way into Star Wars. So you know that it works. I don't have to do anything more to convince you. That process of getting out tremendous quantities of radiation and letting it work on gas and dust is how you tap that tremendous potential of accretion and let it start to shape its host environment. That's how you get to things like this. So I've told you a little bit about the energetics of the problem and hopefully set the scale for you in that sense. But I haven't really told you how it is that you generate the radiation. And that's where some of the more interesting physics actually comes in. It's done via an accretion disk. So here is an optical image of a galaxy that doesn't have a very distinguished name, NGC 4261. If we looked at this with an optical telescope, all you would see here is the white light on the left panel. If I looked with a radio telescope, though, I lose all of the starlight, but I see these huge plumes rocketing out of the galaxy. And if I zoom in to the center with the Hubble Space Telescope, what I start to see here is a disk of material orbiting around this central black hole in that galaxy. We fuel black holes and stars and white dwarfs and neutron stars and anything else that's allowed to accrete, even giant planets, through a disk like this. This is going to be the means by which we squeeze all of this energy out, is in a disk. And I told you that this was a process that happens on many different scales and in very different settings. So here's a black hole at the center of a distant galaxy. Here are actual images of disks around stars just starting the process of becoming stars and planets. So on the left here is a Hubble image of a system called Beta Pic. The star has been blocked out so that you don't lose the details for the glare of the sun. If you imagine trying to see something next to our sun, you obviously have to block out the sun before you have any hope of seeing that something. So that's what's been done here, and you can see this thin disk of material. The planets in our solar system lie in a single plane and generally orbit in the same sense because they formed out of the remnants of the disk that built up our star. So this process that happens around black holes also happens around stars, and it's how you build things up. Now the spatial scale here is large. Each of these tick marks you see in this left image is 100 AU, which is to say 100 times the distance between the Earth and our sun. Jupiter is at 5 AU. The outer parts of our solar system, as we define them, are at about 50 AU. So this is huge by comparison. But here's an image on the right with the Atacama Large Millimeter Array. This is the newest best thing in ground-based astronomy. It looks in millimeter wavelengths, which is great for seeing stars and planets form. And this is the kind of thing that if I showed it to you a few years ago would be an artist's conception of what this process would look like. This is not an artist's conception. This is an actual image of a disk building up a star, and you can see that things are starting to happen. You're starting to sweep material out of this disk with objects that will become planets. So you can see it happening thanks to this fabulous observatory. It's sitting in the Atacama Desert. No recorded rainfall, ever. An elevation of 15,000 feet. Unless you're used to mountaineering, you will pass out. Even maintaining the facility is difficult. It's really an engineering masterpiece, and it's delivering fantastic things like this. But hopefully you agree now that there's disks around stars and around black holes. So we have an idea of how this is going to happen. It's a disk that's going to get all of this working, but a disk has a problem, and I'll explain this, and we have to go back to appreciate this problem. So to understand orbits, we have to go back to Tycho Brahe, a Danish astronomer. He got something like 5% of Danish GDP from the king to build really first-class instruments to monitor the motions of the planets through the sky. 5% seems like a lot, but let me remind you, that was about the cost of the Apollo program. So there's a modern precedent for doing big things like that. He got very good measurements of planetary motions, but he was having trouble interpreting them, so he went and got the best mathematician that Europe had. That was Johannes Kepler. He took a look at the data and figured out that planetary orbits were not circular, but elliptical. And he also noticed this weird thing that within the ellipse, the planets seem to sweep out equal areas in equal times, which is a strange geometric observation to make. Bear in mind, he's only looking at tables of numbers when he does this. He's not looking through a telescope and seeing the entire orbit over a year or something like that. Nor is he using a computer, of course. Isaac Newton comes along thereafter, and he understands that it's force that changes momentum, and that otherwise momentum is conserved. And that's the basis for what Kepler had seen here. Angular momentum is also conserved, and we saw that in that demonstration with the Holberman sphere over there. What that means is that when we look at how planets behave in our own solar system, they obey Keplerian orbits, which means that as things are further away from the sun, they orbit more slowly, okay? So on this axis, I'm showing you the distance from the sun of some familiar planets in units of AU, which again is the distance between the Earth and the sun. What this means is that Jupiter is 5 times further away than we are on average. And this is the average orbital speed of these planets. So you can see that as you get further away, the planets are moving more slowly. So the outer planets have a much longer trip around the sun, in part because they have further to go, and in part because they're going more slowly through that path. This holds true in almost any orbiting system. You can get to this result that Kepler derived empirically by taking Newton's force law here at the top, Gmm over r squared, equating it to a centripetal force, and then it drops out. So if you know Newton's laws, this is a simple, obvious result. Kepler didn't know that in advance. He had to work it out from data. But this is how orbits behave. Things close to the source of gravitation move very quickly. Things that are further away move slowly. And so that tells us something about how these disks work. It means that the stuff that's close is orbiting really, really fast, and the stuff that's further away is orbiting slowly. Or so we think. We can see that happen with planets, of course. We can take many, many exposures with our telescopes and verify this, no problem. You shouldn't take my word for it, though, that this is how disks work. You should wait for verification, and I'll try to offer you some of that now. How do we know that this is how disks actually behave? Well, in part, the gas in the disk glows. This is a hydrogen lamp, and you can see that it doesn't emit white light. It's emitting light at just one wavelength or one frequency, right? Sort of a purplish hue here. And this is just one part of the many dangers that await me as we do this talk. This is 5,000 volts. This is shortly going to be 2,000 degrees. We have a spinning metal disc and a dangerously strong magnet over there. So it gets more interesting in the next several minutes. More interesting for me as well. So this is going to measure the output of this hydrogen gas. And let me rescale this for you. There we go. It's really emitting primarily at just one wavelength. We all agree, right? That's very useful. That's very different than white light, which has emission over many, many, many wavelengths. And in fact, gas isn't just hydrogen in an accretion disk. In fact, it's comprised of different elements. And that's better represented by a fluorescent bulb. Let me again rescale this. So there's some continuum here. There's some thermal continuum emission emitting over many wavelengths. But when we look at a disk, this is kind of what we see. We see some thermal continuum, and I'll show you that in a moment. But we see particular emission at several wavelengths that tells us what kind of elements are sitting in that material. But it can also tell us how fast they're moving, and that's because of the Doppler effect. We all remember the Doppler effect because of train whistles, right? When the train is coming towards you, it has a little bit of a higher pitch, and when the train is past you, it's moving a little bit more slowly. Sorry, it's not moving more slowly. The pitch drops. And it's an effect of the wave fronts piling up as the train whistle approaches you, and the wave front spreading out as it moves away. We can illustrate this with what's called a Doppler whistle. Light works in exactly the same way that sound does in this regard. If I take this lamp and swing it over my head, which I'm not going to do, we would see the Doppler effect in this emission. What we would see is that the lines would spread out into sort of a Viking helmet shape. And the amount by which they spread out tells us how fast the gas is moving in its orbit. But the same thing happens with sound. So this is the noise maker from a smoke alarm. Fair warning, it's going to be loud. And this is a 9-volt battery. It's been some time since I launched one of these into the audience, but you might want to be prepared as you are at a baseball game or something like that, right? All right. So pretend this is a lamp emitting at one frequency the same way that the sound is one frequency right now. Can you all hear the Doppler shift? Then as I go a little bit faster, you can hear it in a more pronounced way, I hope. Is that correct? I'll slow it down again. It's a little closer to its natural frequency. And when I speed it up, you can hear the distinct splitting of the frequencies, right? Good. All right. So light's going to do the same thing. All right? That's how we know that the disk is behaving exactly the way planet orbits do, and that things are moving much faster in the center of the disk than they are on the outside. Thanks, Warren. But we still have a problem. We've figured out one important aspect of disks, that they're faster on the inside than on the outside. But that still doesn't give you light. It doesn't explain why they glow. And the problem is, if they're obeying Keplerian motion entirely, then they're conserving angular momentum, which physics students know as mass times radius, fancy vector cross product times velocity. Or in loose terms, mass times radius times velocity. This is going to be conserved, and unless there's a force that's pushing on a planet in its direction of motion, the planet just orbits in a very stable way. You might have noticed we're not falling into the sun, so our angular momentum is being conserved. However, another way of failing to conserve angular momentum comes about if friction acts. This happens in low Earth orbit satellite systems. The sun has an 11-year cycle of activity. And when it's at its peak level of activity, it causes Earth's atmosphere to puff up just a little bit. That just a little bit of puff is enough to create a drag frictional force on low Earth satellites, and they re-enter. So a likely outer limit lifetime for things in low Earth orbit is about 11 years. Some of them survive solar max, some of them don't. So if we're going to get stuff in and make our star or make a black hole, we have to get rid of the angular momentum. They can't be exactly Kepler's orbits in these accretion disks. We have to change some angular momentum, change some energy, and get the energy out. That's really the trick here. And the answer is the disk has to have some internal friction, and that will get it to glow, that will get it to heat up, that will transfer the angular momentum, that will solve all of these problems that we have. Let me show you, or remind you really, how this works. Awesome. So this is an infrared camera. You can see I'm glowing because it's infrared. You all glow in infrared too, so it's not just a problem that I have. By the way, when you have a fever, we'll talk about this in just a minute, but while I'm on camera it sort of makes some sense. When you have a fever, you have a higher temperature, right? What this means is that you're going to glow a little bit extra in infrared than you do ordinarily. The energy that you lose by glowing a little bit extra through an entire day of having a fever of, say, 104 is about the same energy that you would get from eating an apple. So I forget if the conventional wisdom is that you should feed a fever, but I think you should because you're radiating away an extra apple with your higher temperature. So here are some wood blocks. Friction heats things up and gets them to glow. I'm likely going to do a poor job of this, but let's let these two blocks represent bits of material in the outer part of an accretion disk, where the motion, as we said, was slower, right? Assume there's some friction. So hopefully you can see this. I'll try to get out of the shot a bit. And we'll rub them together. Can you see it heating a little bit? Warren says 10 times, so I'm doing 10 times. All right. So you can see them glowing faintly. If I step out of the shot, the scale adjusts. And if you notice the numbers, you can actually see what the temperature on the blocks is, right? That scale on the right-hand side there is telling you that they're 22 degrees Celsius in the middle where they rubbed. Now let's assume that these two blocks are bits of gas on the inner part of the accretion disk, where things are faster, okay? So I'm going to take these and rub them faster. And you can see the difference, right? The faster motion, owing to friction, is sending out more heat. So the center of an accretion disk is going to glow like mad from that internal friction. Now, we don't have wood in our accretion disks. What we have are magnetic fields. And the thing that causes this to happen is a really interesting effect called a magnetorotational instability. The way to understand this is to imagine that you've got two things orbiting a central mass. And for the moment, let's just say they're billiard balls and they're connected by a weak spring, like a plastic slinky or something like that, that's been played with too much. So it isn't a lot of tug from that slinky connecting them, but a little bit. Now we said that the orbits are basically Keplerian, which means that the thing that's a little closer to the central mass should be orbiting faster, and the thing that's a little further away is going to be orbiting slower. But they have this connection. So what happens? Well, the thing that's interior, called MI here, will drag the outer thing along with it by virtue of this connection. The outer ball or packet of gas will get a little extra velocity. Angular momentum is mass times velocity times radius. This one has to move out. So we're transferring angular momentum out. But this outer thing is also going to pull on the inner packet of gas or billiard ball. It's going to slow it down. It will no longer have the energy required to hold off gravity. It will move in. So this magnetic connection achieves the effect of transferring some mass into the middle of the accretion disk and building up your star or planet or black hole. And it also achieves the goal of moving angular momentum out of the system. This was really a fundamental breakthrough, best articulated by a couple of scientists called Balbus and Hawley, and a lot of people have followed up this work. This is something that's experimentally verified. There are experiments done at different places around the world where they have extremely hot gas with magnetic fields, and they watch it evolve, and they can see that this particular instability develops. So if you like, it's a kind of laboratory astrophysics where you can do a test and see if gas under same conditions as you have in astronomy will actually do this tricky little bit of a magnetic connection making a disk work. And it does. But again, I'd have you not take my word for it. I can show you that magnetic fields are able to create friction. So what we have here is a metal disk, like so. Cool. And I'm going to spin it. Don't worry, although there's a notable absence of a screw on the front, which should unnerve you. It's anchored with a tight screw in the back, so you're okay. It is a good thing, yes. So we're going to spin. Now, this isn't a perfect model for an accretion disk, right? This is a solid, so it's going to rotate like a solid body. And we've just said an accretion disk will operate in a way where the center spins a lot faster than the outer portions do. In an accretion disk, the material is going to be moving like material does in your blender in your kitchen at home, where the stuff that's close to the blades is moving very fast, things on the outside less so. But this is not so bad. So we'll start this moving. This is a bar magnet. Not quite.
This is a keeper.
This is a...
Did you want the small bar magnet? I thought you...
No, it's okay. We'll use the big one. Sorry. If we've learned anything from Mythbusters, it's that bigger and more powerful is always better. This is bigger and more powerful. Watch what happens to the rotation owing to the magnetic field. And do you notice that the disk heats up? You can watch the heat spread across the metal disk. That would happen in an accretion disk too. And if I quickly stop it, I can break it really quickly with the magnetic field. Magnetic fields do create friction. They can change angular momentum. So this is, not a perfect analogy for an accretion disk, but I think it's actually pretty good. And this is all that's going on. You see magnetic friction causing heat. It's causing angular momentum to change. This is really the physics that makes accretion work. So these magnetic fields in accretion disks are going to get the gas to glow like what we call a black body, which couldn't be a worse name because this is actually a very colorful process. You've got the inside of the disk glowing very brightly. If it was optical, it would be blue. And the outer part of the disk glowing less brightly and cooler, it would be red. So this is what an incandescent light bulb does. It just glows because it's hot. In a light bulb like that, you're sending current across a wire that doesn't want current to go across it. The resistance causes it to heat up. Most of the light, as you know, is wasted in infrared light, and only a small fraction is the visible spectrum light that we make use of. That's why those light bulbs are so tremendously inefficient. But it obeys campfire rules. This kind of light does. So the blue parts of a flame are the hottest. And so we can borrow this kind of scheme and know something about accretion disks close to the object, be it a black hole or a star. At small radius, the velocity is high. So we're going to squeeze a lot of light out, and it's going to be more energetic and blue. And conversely, at the opposite extreme, far away, where the velocities are low, we're going to get less light out, and it's going to be cooler and red. Now, the interesting thing about this kind of radiation, properly called black body radiation, is that the intensity, the energy release per unit area, or if we think of it in terms of light per area, goes like the fourth power of the temperature. That's an extraordinarily steep dependence. Physics doesn't have very many dependencies like that. Gravitation goes off like 1 over r squared. That's only 2 powers of radius. This is 4 powers of temperature. That's why it is that when you have a fever, you radiate a lot more energy in infrared light, because 104 to the 4th power is appreciably more than 98.6 to the 4th power. This is a steep dependence that makes big differences of what small temperature differences might occur. And we can play this out in an accretion disk, and what we find is that the temperature in a disk goes like radius in the disk to the -3/4, which is just a little less extreme than 1 over r. Okay? If you want to think of it as 1 over r, you don't have it very wrong. Now we can show you how this works. We've got our spectrometer here again, and we've got a carbon rod. Warren tells me these are formerly used for film projectors, because when you make them very hot, they glow very brightly, and you send that light through the film, and it projects very well. We're going to make it 2,000 degrees. We turn this on. I promise we'll see this change in a moment. It may even catch fire, we'll see. Ah, yeah. Now you can see it glowing red. This is all black body radiation is about. Things that are dense and radiating simply because they're hot, that's black body radiation. So you can see, I need to rescale this. Hot things that are at a higher temperature, glow more at all wavelengths than when the same thing has a lower temperature. But they also have a characteristic peak. So I think the characteristic peak is given here by this green line. Can you see that? Maybe that's a bit optimistic. Maybe it's more like this. So we can say that's where the peak is. Let's turn down the temperature and see what happens. So I'll turn down the current a little bit here. You can see it's glowing less, right? We're getting less emission at all wavelengths. I'm going to rescale here. It continues to fall. And notice that the peak is moving to longer wavelengths over here, which corresponds to redder light. You see how the peak has moved over to the center over there now, longer wavelengths. So this is really all there is to black body radiation. These are the essentials. Hot things glow more at all wavelengths. And when something cools, it shifts to the red. All right? That is exactly the way that accretion disks glow. It's a series of different radii that are each a black body, and you add them all together and you squeeze out tremendous amounts of radiation. For comparison, our sun, the surface is actually just under 6,000 degrees Kelvin. Around a 10 solar mass black hole, the disk is 10 million degrees. Here's where the T to the fourth dependence of this kind of light really helps you win. T to the fourth for the sun, 1.3 times 10 to the 15. An extremely large number, but much smaller than 10 to the 28. So T to the fourth is really the thing helping you squeeze that luminosity out. If we think about it in terms of luminosity, the total luminosity of the sun integrated across all wavelengths is about 10 to the 26 watts of power. It's an awful lot. And it's putting it out mostly in the visible band where our eyes are sensitive. A young star that's just forming, which has a disk around it, glows at a longer wavelength in infrared. But it can put out up to 100 times more energy. 10 to the 28 is 100 times more than 10 to the 26. That's a little flavor of what accretion can do. It can make a young star 100 times brighter than a normal middle of its life star. And it gets more impressive when we get to black holes. A stellar mass black hole can glow 1,000,000 times brighter than our sun can, and it's putting its energy out in X-rays, not in optical light. So each photon has the potential to do a lot more damage. We'll talk about that. And a supermassive black hole, 10 to the 38 watts of power, that's 10 to the 12 times a star, which is interesting. Remember, 10 to the 12 is a trillion. We have about 300 billion suns in our Milky Way, putting out light, by and large, mostly in the band where we see. A supermassive black hole is going to be putting out more than that at a shorter, more energetic wavelength, an ultraviolet. So a black hole that's really swallowing matter, and in this regard, perhaps we should be grateful that ours is not, can outshine its host galaxy. Kind of fantastic. Now I think you begin to see, we've talked about how do you generate that radiation. How do you get something so small to have such an impact? It's because you can squeeze out tremendous amounts of radiation through accretion. So here's a temperature scale and a wavelength scale for the different kinds of radiation that we've been talking about. Our sun is over here, 6,000 degrees. It's primarily yellow. A black hole disk around like that in our Milky Way, 6 to 7 orders of magnitude more massive than our sun, glows primarily in UV. And the reason that's important is that optical light can't break apart or ionize hydrogen, but ultraviolet light can. It can take the electron off of the nucleus. It's very efficient at heating gas. The X-ray emission that comes out of these disks is about 1/10 of the UV. But X-rays can even tear apart iron, which holds on to its electrons more strongly than does hydrogen. So it's very, very good at heating gas. And the reason that's important, when we look at a galaxy like Andromeda, this picture shows you different colors. We can't see every individual star in this picture. They're kind of smeared together by light scattering. The blue outer parts of this galaxy in the spiral arms are where new stars are being formed. New stars tend to be hotter and therefore bluer by the laws of black-body radiation that we've just talked about. But to form new stars, the gas has to cool. If it's hot, it expands. This is just sort of hot air balloon physics, right? To get things down and to gravitate and to make new stars, the gas has to cool. It can do that out here, but somehow in the center of these galaxies, all we have is really hot gas and old stars, which are cooler and more yellowish red than the ones on the outside. And a major problem is, how does that happen? How do you feed all of that hot gas into that region? How do you stop stars from forming in the center parts of galaxies? And the answer is that the black hole is helping to do that. It may not be all of the story. This is still an area of active research, but it's likely having an important role in putting lots of hot gas in here and stopping nice young blue stars like these from forming in the center of galaxies like Andromeda. How do you get to that point? Well, Andromeda is sort of like our Milky Way. It doesn't have a very active black hole in it. It doesn't have an active accretion disk feeding it. But this is the Circinus galaxy, a picture taken with the Hubble Space Telescope. And you sort of get the idea here that you're peering over the edge of the disk. And you can see the light pouring out from the innermost part of this galaxy. And you can even see things, gas getting flung out. That's the hot gas that's getting launched out by this accretion process. Another good example also with Hubble, here again, not an elegant name like Andromeda, NGC 4438. You're kind of looking over the edge, and you can see that there's these plumes emanating from this actively accreting black hole in the center, shaping the host environment in that galaxy. And then when we let that play out on the very largest scales, you end up shaping galaxy clusters, and that's what you can see here. So here's a central galaxy. This is what it looks like in optical. If we look in radio bands, we see these huge plumes being shot out by the black hole. This is the X-ray image. So you're really reshaping host galaxies and even clusters of galaxies through accretion. And hopefully I've managed to give you a small flavor of how that works. So I think I'll leave it there, and thank you again for coming, and thank you to the demo lab staff.